right. Hi, everyone. This is Dr. Vogel. How are you? This is a problem-solving video for SCMH 1013, Concepts of Science Online. Okay. And we're just going to go through some problems in Chapter 2 and subsequent chapters that you may come across on quizzes, just so you have a sense of how these are solved. Okay, so one of the first questions you might get asked is something like a car is traveling 30 miles per hour, all right? And how far do you go? How far do you go in 15 minutes, all right? So for 30 miles per hour is a velocity, and velocities are calculated as distance divided by time. So miles per hour would be something like, it would be written like this, all right? It would be, that was how you'd write it in fractional form. The book also talks, says that velocities can be measured in meters per second, but 30 miles per hour is something that you'll see in your car odometer and what have you. Okay. Now we all know that that we work in hours, more in minutes and hours than we do in seconds in our everyday life, and so we all know that 15 minutes is equal to about 0.25 hours. All right. So 30 miles per hour is going to be 30 miles in 0.25 hours, all right? And sorry, this is not the way to do it. All right. What we're going to have is 30 miles per hour is equal to distance, which is the unknown here, and the time that we traveled it is 0.25 hours, all right? So we multiply this times this to get distance, all right? And here's a very old-fashioned device times that known as a calculator, and we can see that when we multiply that times that, all right, we get 30 miles per hour times 0.25 hours, so the hours cancel like so. All right, and we get 7.5 miles. All right, so that's how you do velocity. Velocity is distance over time, okay? Sorry about that. Let's look at some data here in terms of Lab 4 talked about position and velocity and acceleration. And it talked about the relationship, especially the graphical relationship between these, all right? So we did these experiments where we rolled a ball down a ramp, okay? And then when I did the experiment, I more or less got data that looks like this. Hopefully you've turned in all these answers. But for the left-hand side, we have distance in centimeters, and on the right-hand side we have time in seconds, okay? So for this first reading, with velocity equaling distance over time, I get 10 centimeters in 1.1 seconds, all right? So more or less that's going to be about 10 centimeters per second. I think if we actually do it on the calculator, we'll get, it looks like 9.09, okay? So there's, you see the exponential effect, but 9.1 centimeters per second. So that's velocity 1 is 9.1 centimeters per second. What can be tricky about velocity is that you can measure it in your car, you measure it miles per hour. But when you're doing this experiment, you did centimeters per second. You could do meters per second. You can do, parsecs per light years, all right? So you can use different numerator and denominator as long as the numerator always is a unit of length and the denominator is always a unit of time, okay? So if we came down here and we looked at this velocity, this was going to be velocity 1, and this would be velocity 2 down here. So it took 2.8 seconds for the ball to roll 60 centimeters. That was the entire length of the ramp that it rolled. And so for that, this is going to be V1, this is going to be V2, is going to equal 60 centimeters divided by 2.8 seconds, all right? So plugging that into the calculator, we get 60 divided by 2.8, all right? And there we have 21.4 centimeters per second, all right? And we see that V2 is quite a bit, almost twice as fast as V1, all right? So these are your positions up here. So here's your position, and here's your times. So we sort of, you investigated position, and then we've looked at the change in velocity, and you guys plotted that. Now I'm going to show you how to calculate acceleration using two different velocities, a final velocity and an initial velocity, because an acceleration is a change in velocity, all right, and velocity is a change in position with time. So you can see, if you ever end up taking calculus, you'll see these in more detail, but all of these have this relationship. And the velocity is about a change in position, and then with time, or change in distance with time, and then acceleration is a change in velocity in time. So these have a special relationship that you study more in calculus. But here, to talk about the change in velocity with time, what we do is say V2, which is 21.4 centimeters per second, minus V1, which was 9.1 centimeters per second, all right? So this is the difference. This is V2 minus V1, and then you divide that by time, okay? So this is going to give you your acceleration, and by the way, this is equation on page 34 of your book. 34 of your book. Okay, so the time in this case is going to be the time that the ball took to achieve this change in velocity, okay? So what we're going to do is we're going to take the time at which it was traveling at 10 centimeters per second, all right? That was at 1.1 seconds in this system, and we're going to subtract that from the time it took to achieve the velocity of 21.4 centimeters per second, all right? So this time, we'll come over here, and we'll say time is equal to 2.8 seconds minus 1.1 seconds, okay? And that will give us, I think I can do this one in my head, 1.7 seconds. So it went from this velocity V1 to this velocity V2. You can go back up here in this table. It went from you know, at 60 centimeters it was at this time, and at 10 centimeters it was at this time. So those are the respective times. So this will be, let's make sure we do this accurately. We'll get 21.4 minus 9.1, and then we'll divide that by 1.7. All right, so the t is equal to 1.7, and here's our acceleration. So our actual acceleration here is going to be 7.23. So let's call it 7.2. Now up here we have centimeters per second. All right, and down here we have seconds. So acceleration in this case is going to be centimeters per second squared. Okay, so it accelerated by that much in this amount of time. Okay.